Okay, right, okay. So yeah, just for those who don't know who I am Mark. I am an Azure MVP, and I have no job title really. Nobody has ever given me one. I'm just a freelance Azure consultant, but I kind of come from a developer background. I've been coding stuff. People have been paying me to code stuff since the 1980s, and I have been occasionally referred to as a cloud solution architect more recently. So I'm a developer with aspirations. Right. So what I'm basically going to talk about today is, we'll start on the noddy stuff. We'll just talk through a bit about why services and microservices and that sort of thing. Then I'll talk a bit about Kubernetes and containers. Then I'll talk a bit about serverless, specifically functions as a service. And then we'll talk about running serverless on Kubernetes. So we start off in the beginning with the monolith. So essentially people would build one big lump of deployable code, and they would throw that over the wall, and it would land on the server, and it would run, and it would probably talk to a database server somewhere. If you were really lucky, there would be 3 tiers to it, and that that was very popular for the longest time, and still there's plenty of people do it, and for small and simple systems, it's still a perfectly good way of doing it. But these days we're looking more and more at this sort of thing. So we're talking about services stroke microservices, and for my purposes here, I'm going to just think of a service as something that's individually deployable and individually scalable. So in this section, in this case here, we've got some sort of fancy e-commerce system, and there's a checkout service over here, and a cart service over here, and an actual website over here, and a product catalog over here. And the basic idea is that if you want to update your shipping detail, shipping information, to add a new shipping service, that has nothing to do with your cart or anything. So you don't necessarily want to deploy your shipping service and have to redeploy your cart at the same time. Also, if your website's particularly busy because it's Black Friday or something, then your catalog service is going to get very heavily used, whereas your payment service is probably not going to be as heavily used. So there's benefit to being able to scale up your catalog service larger than your payment service. So that's where people have started to go. Some people have taken this to extremes, and Uber recently have said that they'd gone to thousands of microservices, and they're now trying to roll it back because the management of that was just too outrageous. But most things these days are split up into a number of services, and the ones that aren't are certainly thinking about going that way. I'm working with 2 clients at the moment who are both doing this. So what do you do with where do you put your services? The first place people started putting services was in containers. The basic idea behind a container, obviously, is that you can package up your application, your service, into something which is almost like a tiny VM. Now, it's actually a process, or at least a Hyper-V abstracted thing in the case of a Windows container. But essentially, it's your application and all its dependencies packaged up into this neat thing that can be then deployed out, into your development environment, your production environment, your testing environment, anywhere that you want to run it. And in theory, it runs exactly the same because it's packaged up with all its dependencies. It has no reliance on the host that it's running on, so it doesn't matter what version of .NET framework you've got on there or anything like that. The other thing about containers is, they are generally speaking transient. So, they can be long running, but you would tend to assume that a container is either not going to run for long deliberately, or that it may get thrown away at any point. So, you design them to be resilient. And they're particularly good for lift and shift scenarios because all a Docker file is, so if you're assuming you're running a Docker container, all the Docker file is essentially just a list of lines that says, use this operating system base, install this on top of it, pull in these files, and then run this command to start it off. And any application can be built in that way. So anything you've got there, got running there, which can be deployed by itself, can be dumped into a container and run somewhere. Now, the next thing we want to do, we've got our individually deployable service here in a container, but we then want to make it individually scalable, and that's where the big ugly Kubernetes comes in. Kubernetes, originally came out of Google as Project Borg. The idea behind it is that you've got all these little containers here running in what are called pods. And Kubernetes' job is basically to orchestrate them. So essentially, what Kubernetes is a defined state system. So at the end of the day, in the Kubernetes database, which happens to be etcd, you're storing your desired state of what containers you want to run, how many of them you want to run, what sort of requirements they have, how much memory they need, will they need a GPU, all that sort of thing. You set that up through the Kubernetes API. You then have what's called a controller manager, which looks at the current state of your system and the defined state of your system and works out how to change the current state of your system to the defined state of the system if they're different. And then the scheduler, which then feeds out to the actual nodes to tell them what they should be running. Within each of those nodes, you've got the kubelet, which is the sort of overall controller for that node, and usually a node is basically a VM. You've got cAdvisor, which is the thing that keeps an eye on the node and produces your metrics and stuff. And then at this end, you've got a proxy. So when somebody comes in from outside to actually access one of your services, the proxy knows which pod contains a container that can service the request for that service. Now, the other thing you'll notice here, which we'll come back to later, is a pod can have more than one container in it. So generally speaking, you'll have one container which is your container, but you can also have what are called sidecar containers, which are ones that can be injected into pods on request and provide services. So, for instance, you can inject a reverse proxy in there so that when a request comes in, it goes through the reverse proxy to your container, and you can then manage, do management and logging of the network traffic and such like. That's, if you've heard of service meshes, that's basically what a service mesh is doing. So that's Kubernetes. That's about as simple as I can make Kubernetes, and there's an awful lot of stuff if you're doing real things with Kubernetes, which you have to add on to that to make it safe and fun to run in production. But that's the essential Kubernetes story. So you've got a number of VMs running your containers, and Kubernetes is trying to make sure that as your requirement for things changes, that it has the right number of pods running in the right number of places to provide the right amount of service for you. Now, the actual scaling part of Kubernetes is works. There's a couple of different things in it. Within your VMs, within your nodes, you've got a number of pods. And your pods get scaled by what's called the horizontal pod autoscaler. By default, what that does is it goes in, looks at the metrics that are coming out of cAdvisor, which are coming from the pods, looks at those, usually CPU and memory based, and if it decides that there is too much CPU and memory being used based on whatever criteria you've set in there, whatever thresholds you've set, then it will fire off to the deployment that it needs more pods or fewer pods and change the number of pods accordingly. So as your services get busier or quieter, within the context of your overall VM, within the context of your overall cluster, it will spread that load between them. The other thing is when you're running in a cloud environment, so in AKS or in AWS, you'll also have some sort of cluster autoscaler, which works at the node level and allows you to fire up new VMs as you run out of space in the pod, you run out of pod space in the VMs. So if your VM itself is overloaded with CPU or memory, then it will scale out more nodes for you. Just worth mentioning, by the way, since this is an Azure thing, if you're using AKS, then all this bit over here, even though there's actually nodes going on here and VMs going on over here and data, that's all included for you so that all comes for free. So it's only the actual nodes, the VM load that you're paying for. I should say, by the way, if anybody has any questions at any point, feel free to either come off mute and ask, or just drop them in the chat there. I have a separate window open with the chat, so I should see them fairly quickly. And if I don't, I'm sure Alan will shout at me. So if anybody has questions about Kubernetes before I move on to the next bit, now would be a great time to shout. Otherwise, I will assume that everybody is following completely, and we'll move on to serverless.
Just before you move on there, I think there's probably someone in the channel here who has their mic turned on. We can hear some background noise coming in.
That's better.
Oh, that's much better. Was it you?
No, it wasn't me, but somebody turned it off. So.
Okay, awesome. Let's continue. Thanks, Mark.
We'll draw a veil over that to protect the guilty. Right. Okay. So now we've got our Kubernetes service there running containers, and we can scale up and down our VMs. But now we move on to sort of the more modern way of hosting services, which is serverless. Now I'll just return to this slide briefly because I just want to talk about something which is quite important about serverless. Now the thing we didn't talk about before was all these lines flying between all the services as they communicate with each other. And the thing is, there's two ways they can be doing that. They can be doing that synchronously or asynchronously. So in the synchronous case, we've got essentially an API-driven thing. So if somebody places an order in this sort of scenario, then we could potentially have customer places an order, the order service takes that and says, okay, we need to create a shipping, we need to get some shipping for this order. So it calls out to the shipping service. The shipping service calls out to the inventory service to make sure that there's enough inventory for it. It goes off and then calls the label printing service, which will print the labels and sort out the packaging. But in a stand, if we'd had all this synchronous, then obviously if the inventory service fell over, or if the label printer was sort of somehow foobar, then that could potentially feed up, and the order would not get placed because everything would go wrong, or at least you wouldn't know that the order was placeable, so you'd have to come back to the customer and say, sorry, problem, please try again. So and if anybody was in the session that Duncan did on track 3 earlier, we'll all know that ideally, where possible, you should be making your services talk to each other in an event-driven manner. So rather than when your order comes in, you're sort of waiting for all the rest of the things, you just fire into a queue somewhere of some sort, a thing that says, okay, here's the order, here's all the information about that order. Sort of that order is now done, and then any service that is interested in doing something when an order is placed can then go off to that queue and pull that information. So the shipping service, when it's ready, can go and pull the next order off the queue and go and do stuff, and then it will probably go and fire off another thing to the inventory service as an asynchronous thing that happens. And so everything becomes nicely decoupled. It makes it a lot easier to deploy your services individually, and the whole thing becomes a lot more resilient. So as a side effect of running event-driven stuff, you can actually make systems that are fully event-driven. So I've made a thing that does stuff here, but in theory, you could have a browser out here, calls through to an event-driven service. The event-driven service tells another event-driven service to wait for something to be done. It then fires off to a Cosmos database to save the information. The Cosmos database saves the information, and then its change feed fires off more services down here. So one service could fire off a notification somewhere. Another service could then save off to cold storage. And And then once that's been safely saved, it can fire another request back up here that says, OK, go off and say that this request is finished. This can be then using an asynchronous HTTP pattern to say, OK, I now have a reply. And back here, another service could then be firing off another queue message to go off and do all sorts of other stuff. But there you can get a completely asynchronous, event-driven thing where your browser comes in, places an order or whatever, and everything starts bouncing around the system. And if you're event sourcing, then your Cosmos database here has saved all that information off so that you can then replay all your replay your system from the events and do all the great event sourcing stuff. And these little arrows, that these little lightning bolts here, that the services are, of course, Azure Functions. And the way Azure Functions work is they are purely event driven. So an Azure function is just a piece of code, an actual code function, but it runs when something happens. So when something comes into a queue, or when an HTTP request comes in, or potentially when an email comes into an exchange or something like that. And anything that happens that can fire a function, and the function will run. It will do its thing. It will kick off whatever it needs to kick off as a result of that, and then it will die again. So importantly, it's always an ephemeral thing. It never runs for more than about 10 minutes, or in certain cases, it can go up to an hour. But it's never going to live for a long time. It's always priced by the amount of time it runs. So if it runs for 5 seconds, you'll get paid, charged for 5 seconds of CPU time. If it can get done in less than a second, you'll get paid, charged for less than a second of CPU time, and you'll get charged a tiny amount for the amount of memory that it's using. But any time that function isn't doing anything, you're not paying for it. There's the reason it's called serverless is because the infrastructure is essentially invisible to you. There are servers under there, but you're not really you don't really care about them. You're just firing your code at the cloud and saying, please run this code when this code needs to run based on whatever events it cares about. You provide the framework, you provide the servers, you provide the network. I just want this code to run, please. So you end up with a very low management thing there going on. It's very low cost and it's very highly flexible. In theory, if you've got nothing going on, then you don't pay anything and you've got no servers running. But as soon as work starts to come in, then the serverless infrastructure behind that will run as many instances of your function concurrently as it needs to process all the work that's coming in. So as long as it can look at your events, so for instance, you've got a queue, it can look at your queue, say, okay, there's a million events in that queue. I'm going to fire up a hell of a lot of functions to process all those as quickly as possible. The downside, of course, is that if you're running serverless, then you're kind of locked to whatever it is your platform provides. So, for instance, AWS only has a certain number of runtimes that it will support. So it will support .NET, it will support Node, but if you've got an old COBOL system, it's not going to support COBOL. If you've got a new Rust system or a Haskell system, it's not going to support Rust or Haskell. Also, the things that trigger your events, your functions, have to be things that have come out of the box in that platform. You can't write your own trigger to say, I've got, if you wanted to trigger off a RabbitMQ or something like that, which isn't one of the cloud platform services, then you probably won't get that, or potentially won't get that as something that you can trigger off. So you are kind of tied down as soon as you head towards this sort of Azure Functions, Lambda, Google Cloud Functions side of things. You are tied to whatever your platform gives you. So that's where we come to Kubernetes versus serverless. And anybody want to butt in with any questions at this point before we move on to the next section?
Boo, I love Kubernetes.
That's an interesting question. Right. Okay. So for a while we had this dichotomy. You had the containers people running Kubernetes, so they could run anything. They could run it anywhere. The nice thing about Kubernetes is you can run it on a Raspberry Pi if you want, but you can also run it in the cloud. You can run it on your laptop. You can run it in a data center. It will run just about anywhere that you can run Linux. It's on the other hand, it's not terribly elastic. So you end up with a kind of fixed cost usually of the number of VMs and nodes that are behind it. Your elasticity was limited to, scaling up extra VMs and scaling them back down. So, if you've used the traditional app service type thing in Azure, it's, very much like that, and, you don't get any help. Everything that goes into Kubernetes is in a container. So you're coding it yourself. And as we've seen, sort of Kubernetes, even at the very simplest level, has, a relatively complex infrastructure thing going on behind it. On the other side, you had serverless, where, you're locked into your cloud, essentially. You have a number of restrictions placed on you, but if you're willing to accept that lock-in and those platform restrictions, then you get very elastic cost. You get very elastic performance. You get your triggers and things provided for you. So, you don't have to write any code to talk to an Azure Service Bus or anything like that. You will just get the message shoved straight into your function as a string or as an object. And, there is basically no infrastructure to think about. You just deploy it to Azure Functions and it says, OK, I'll run that for you. So that was where we were, and there was a lot of argument about whether containers or serverless were the better thing, and then somebody started thinking, why not both? I think that person might actually have been Brendan Burns, but don't hold me to that. So the way people had been running, if they wanted to run containers and serverless at the same time, they would have an AKS cluster running, and they would have a separate Azure Functions service or services running. And when the services in AKS needed to talk to the services in Azure Functions, they would have somewhere in the middle either API calls or service bus or something like that to connect the two together. But of course, that means there's a lot of people out there who are looking for cloud agnosticism or just the simplicity of being able to take one thing and do it the same everywhere. Again, I'm working with a client at the moment who are, have been traditionally an AWS shop, but they have a customer who will not let them run on AWS and is requiring that they run on Azure. Now, they have the advantage here that they use Kubernetes for all their infrastructure and all their deployments. So the cloud is just a place for them to run Kubernetes. So they need very little change to actually be able to run exactly the same stuff up in Azure. So what we can do now is to actually take our Azure Functions and our serverless functions and potentially our messaging services and just run it all in Kubernetes, all in one go.
Sorry, guys, there's somebody talking there. Can you please mute your microphone?
Okay. So I thought it was a question for a minute, or somebody laughing at the animation.
No, it's awesome. Thank you.
Anyway, so that's the way a lot of people are starting to look at this now. Now I should point out that what I'm going to go into now, which is running serverless on Kubernetes, it's still got compromises. If you can run, if there's no reason for you to not run your serverless stuff in Azure Functions, then run your serverless stuff in Azure Functions, because the consumption plan, the infrastructure that runs behind that is highly tuned to run serverless stuff. So you'll be more flexible, more responsive, more scalable than you will be able to if you run in Kubernetes. On the other hand, if you are in one of those situations where running in Kubernetes, purely in Kubernetes is an advantage to you, then this will get you very close to where you would have been in Azure Functions. So the first thing, AKS specifically here that we should talk about is what's called AKS Virtual Nodes. This is based on an open source thing called virtual kubelets. Now, if you remember, the kubelet was the thing that ran inside a Kubernetes node and provisioned all the pods and stuff in it. Now, what a virtual node allows you to do is to say, okay, I don't want my node to be a VM. I want it to be something else. And so there's no sort of similar service in Google, as far as I know, but in Azure, that we can use virtual nodes and virtual kubelets to run up node containers in Azure Container Instances. And in AWS, you could do Fargate, and there's a number of other providers. But what that essentially allows you to do is say, rather than having a VM, I just want you to use Azure Container Instances to provision my containers from my pods. And what Azure Container Instances is, it's a service in Azure that basically is the simplest possible way to get a container running in the cloud. So there's no ceremony to it. There's no fancy reverse proxies around it or anything like that. It's not even as complicated as running up web app for containers in app service and saying, please run this container in an app service. It's just, please run this container, give it an endpoint, close it down when it's done. And it's designed to be very quick to spin up a container, run it, and shut it down. And of course, being a cloud service, you can run as many containers in it as you want. Well, when COVID hasn't shut down Azure, you can run as many containers in it as you want. Also, it's charged purely again on the amount of memory and CPU that your container uses for the amount of time that it's running. So you can see that it's giving you something very similar to the serverless consumption plan type thing of running something, charging you for as long as it's running and then getting rid of it. But we still have the thing of we need to be able to work out how to scale that out. If we're doing it with the horizontal pod autoscaler, it will watch the CPU and memory, and once a container is busy, then it will run up more. And at least this way, we don't have to run up more VMs, but it's still going to be quite slow because it's going to be very reactive to what's going on rather than proactive. So that's where the product called, well, not the product, the open source project called KEDA comes in. This is Kubernetes event-driven autoscaling, and it's on there on GitHub, and it was set up by Red Hat and Microsoft, but it's certainly not only a Red Hat and Microsoft project. And what it's designed to do is to do that sort of thing that you would have got from a trigger in Azure Functions or in some other serverless thing. So it will try to watch the work queue that's triggering your code and proactively take that, turn it into a custom metric and feed that custom metric into the horizontal pod autoscaler to tell the horizontal pod autoscaler how many containers and pods you're going to need, not how many it looks like you're needing because you've got so busy already. It also allows you to scale down to 0, where the horizontal pod autoscaler normally only lets you scale down to 1. So that it works very well with virtual nodes, and it is now a production product. So it has passed version 1. It is GA. It got released, I think, at KubeCon this year or last year. But it's now a thing that you can use in production, and people are using. And essentially, the way it works is you've got your work coming into a queue or whatever somewhere here. KEDA will watch that trigger. It will create a custom metric and feed that into the horizontal pod autoscaler. This bit up here is really just the bit where you feed into the CLI and say, okay, I want KEDA to run in my Kubernetes cluster, please. So the horizontal pod autoscaler then scales between 1 and n, depending on so how many pods it thinks it's going to need to process that amount of work, and you will have defined roughly this how much work requires an extra pod in your definition. And then if KEDA sees there's no work in there, then what it will actually do is to turn that pod off entirely, and then when it sees work comes back in, it will then turn everything back on so it can start scaling up. So if nobody has any questions at this point, I will do a quick demo. Excuse me, I should have got a glass of water. This is going to be the simplest thing that possibly works. So all it's going to be doing is setting up a service bus queue, and that service bus queue will be consumed by an Azure function stroke pod, which does a thing and processes all the messages in that queue until it's done and then gone. So this really is a very simple thing. And this is the way it works. So I'll just quickly walk you through the deployment script here. So if we ignore the ceremony at the start there, so we're going to create a virtual network. We're going to create a subnet within that our virtual nodes can live in. Create a service principal that allows us to create the virtual nodes. Then we just use the Azure CLI to create a cluster there with all the stuff we need. We enable virtual nodes on that cluster. We connect to it so that we can use queue control. Going to create a couple of service bus queues there, fetch their connection information and save it into the Kubernetes secrets. Helm is the package manager essentially for Kubernetes. So we're going to update our package manager repos, and then we can use it to install various things that we'll need, like KEDA. So here we're just saying, please install KEDA on my cluster. And then at the end of that, we have an up and running Kubernetes cluster. Now, obviously, I'm not going to run that live here because that takes 5 to 10 minutes and we ain't got time for that. But once we've done that, then we can do good old YAML, the thing that defines everything in Kubernetes. So this is essentially my desired state of Kubernetes in here for the thing that I want to do with KEDA. And what I have here a KEDA worker project, which is actually an Azure Functions project, which is based on a service bus trigger that says when a message comes in on a service bus trigger on this KEDA work queue, I want to run this function here and pass that in as a message. So if you've not seen an Azure function before, this is literally it. This is an Azure function. It's a code function. That message that comes in there as passed in as a parameter is the message that came off that service bus queue. But Azure Functions has taken care of that. And we're going to do something here and then give up. There was something I was going to say there. It wasn't important. Yeah, that's it. Azure Functions also have the ability, as well as being deployed directly to a consumption plan just as code. There's also, as in the Azure Functions CLI, you can package any function up as a Docker container, which is how we can then get this provisioned into Kubernetes. So if we go back here, I've put that into my Azure Container Registry as a thing called KEDA Worker as a container. So here in my Kubernetes deployment, I'm basically telling it that I want to run that container. It has those limits on the CPU and memory. These are the environment variables that define how it's going to run. And this bit down here is telling me that I want it to run on a virtual kubelet. And this toleration means that I'm going to allow it to run on virtual kubelet, even though virtual kubelet by default won't take any pods. And then down at the bottom here, I've got the actual KEDA configuration. So again, we're saying this is an Azure Service Bus trigger. So it's going to look at that queue in the service bus with that connection string. So that's the thing that it's going to look at to work out how much work's coming in. And those are some configuration values. So we're going to say that, I want to scale between 0 and 5 pods, and I'm going to poll it every 10 seconds because I'm a demo and I want to poll it nice and quickly. So if we come over to the terminal here, there is the current state of my Kubernetes cluster. So basically, it's just got some system type pods in, which we'll see more about later. But what I can do now, this is just, this load work thing is just a little thing I wrote, which will just basically load some messages up into that queue. So I'm going to put 100 messages into the KEDA work queue. And you can see as soon as those messages go in, KEDA picks that up and starts to create a pod. So, we've now got one pod running there, which, sort of will shortly start processing messages off that queue. And then it looks and sees that, there's still messages there, so it starts creating more. Now, so it takes a short while for the actual container to spin up in those, so that's why we're not getting immediate processing. But there you can see it's starting to process that down now. So what we'll end up here eventually with is 5 running pods, each processing approximately 1 message a second. So if we give that a short delay, we'll start ticking down there. And if anybody's not following what's going on, this is a perfect time to unmute and ask. So let's be slow. So that comes off, and then you can see as soon as that goes back down to 0, it says, okay, there's no work, so I'm going to turn off all those pods, get rid of them again. So we go back down to 0 pods. So that's essentially an Azure function running in Kubernetes, but running properly serverlessly. So it's running in virtual nodes, so virtual nodes, and you can then that can create as many pods as it wants, and you only pay for the amount of time that they're running. Right, so we'll go back to the slides. And we'll go a little bit further now. So the next thing we want to do is, that was still running an Azure function. So we're still kind of tied to the Azure Functions runtime, the Azure Functions bindings and stuff. What we can do now, though, is to get out of the box a bit. This is where Dapr comes along, and I think there might have been a Dapr talk already at some point. But this is another project. Actually, comes out of the Service Fabric team originally. So again, it's a fully open source project, and there's a lot of people working on this. In fact, that slide is out of date. This is since it is now version 0.6 or 7, I think, and still moving fast. But this comes out of the Service Fabric team, because the Service Fabric team had been working on things like sort of what do they call them, the resilient and distributed dictionaries and queues and things. So that for services that are running Service Fabric, they provided software around that to help you provide services to your distributed services. So what they've done is they've extracted that from Service Fabric, so it's not dependent on any runtime, and it can provide, it can run on anything you want. And the way it works is it runs as its own container or even process. And all it requires is that it runs next to your service. So in the case of Kubernetes, it runs as one of those sidecar containers that you saw. And it talks to your container via HTTP or gRPC. So it's nicely tightly bound, and it will provide lots and lots of services then to your service. Now, because it talks over HTTP and gRPC, it can talk to any container that understands HTTP, which is all containers. And it doesn't care whether you're running Rust or Haskell or COBOL or what have you. It will just talk to you over HTTP and provide whatever services are required. And there's lots of things it does. So it provides things like talking between different services. It provides state management. So if you want to have a nice, easy Redis backend, for instance, to all your services, but you don't want to write any Redis code, you use Dapr with with a Redis plugin, and so you can then just talk to it and say, okay, persist to this value to my to my shared state, and Dapr will go off and shove that in Redis for you. In particular, what it has is all these resource bindings and triggers. So I was talking about RabbitMQ before. Dapr has a RabbitMQ binding, so it will be able to call into your service through HTTP anytime something comes in on a RabbitMQ queue. And it will work with Service Bus. It'll work with sort of the AWS queues. It will work with GCP queues, and with a whole lot of other stuff as well. So essentially, Dapr provides you with a lot of other stuff. So you get tracing and state management, all that sort of stuff built in. But specifically, it provides you with the bindings and triggers that Azure Functions gives you, but because it's a pluggable system, you can use anybody's third-party provider here, and you can also write your own providers. So if you've got your own event source that you want to use serverlessly, then you can do that through Dapr. So that's really scratching the surface of Dapr. There's a lot of stuff you can use Dapr for in any service-based architecture, whatever it's running on. But for this scenario, it opens up that serverless triggering event-driven stuff for you. The other thing I want to talk about here is the infrastructure, because even when you've got that far, you've still got that thing of Kubernetes being something that really, speaking as a developer personally, I don't like provisioning Kubernetes because I know I'm going to do it wrong, and I know it's not going to be secure if I do it. So, it has to go off to some ops people to actually sort that sort of stuff out and get that done and get the service mesh set up right and all that sort of stuff. And I don't want to have to worry about that really. But on the other hand, I do want to to define what services are in there, how they scale, what resources they're going to need, and all that sort of stuff. And that's where the open application model comes in. This is a project that actually has been originally set up by Microsoft, and in this case Alibaba and Ali Cloud, and it's basically designed to split up the responsibility for your application so that the developer can define the application. The application operator can then define that at a more generic level, but then the application operator may be the same as the application developer, and then that gets handed off to the infrastructure operator, who may be somebody in your company, but may equally just be somebody who works for your cloud provider or for your infrastructure provider. And basically, you provided them with your application and its configuration and its components, and then they can dump it onto any infrastructure they want in theory. That it could be Kubernetes, but there's it could be equally Service Fabric or App Service, or something else, or whatever they've got running in Alibaba that isn't isn't one of the Azure things, and still be able to deploy that out. And essentially, it still works as YAML, but you're just defining, in a sample one here, you're just defining what for each section of your application, what it is. So essentially, what parameters it takes, what ports it needs open, so what environment variables it's going to need, and what the actual container image is. And then you can also feed in things like for each workload, is it a server workload? So it's got a it's got an HTTP endpoint that people are going to be calling into, or is it a worker workload which is just sitting there not talking, just doing its thing but not talking via the network? Or is it some sort of task or singleton type thing? And you can also say, okay, I want this thing to be auto-scaled, a manual scale, or you can set up ingress and storage volumes as well. But you can use that to define your application and say, okay, I've got this container which needs to auto-scale. I've got this container which needs to be a singleton. I've got this container which I want to manually scale between 1 and 3 instances or whatever. And the idea behind this is that I as a developer can define my application, put my code in a container, and then hand that off to the infrastructure person. Now, this is currently work in progress. They're only up to Alpha 2 at the moment, but this is something we need. I think we need to be keeping an eye on for. And talking specifically about Kubernetes here, then there are a couple of projects. There's one called Rudder, and there's one called Crossplane OAM. And what they do is they take your open application model and allow you to deploy it into Kubernetes, and it comes out as a definition of volumes and services and endpoints and jobs and all the rest of it. Excuse me. So I'll do here, I will do a quick demo of doing the same sort of thing as we were doing with KEDA there, but also taking out the Azure Functions side of things and using Dapr and OAM. So in this case, here's our YAML this time for this one. Now you can see here, we're still doing the same basic thing. So all this is kind of the same thing, but this time we've got Dapr enabled. So, and I'm telling it that I want to talk on internal port 3000 between the two containers in the pod. And down here, I've still got my KEDA thing still working off the same thing, except this time we're working off a queue called Dapr work. And then up here, we've got a Dapr work component, which is telling us that we're going to set up a binding that Dapr understands. So as well as KEDA watching that queue to know how much work there is and how many we're going to need, this is defining essentially our trigger that we would have had in Azure Functions to say that, this is a service bus queue and this is something that we want to call through. And it knows by the name, the metadata and the name there, which container it's going to call through to. The actual code here is just world's simplest node app. It's going to listen on port 3000, and every time it gets a request through to /Dapr work on port 3000, it's going to process it. And again here in our request, that request has been set, to contain the message that came through from the service bus. In this case, it's going to be coming through in cloud events form. So that's sort of the industry standard format for events that happen in the cloud. So that will come through with the body of the message in there. And so it does exactly the same thing, returns an OK, and there's tiny little bit more ceremony, but we've got the same basic thing going on. That's our function. That's the thing that responds to the trigger that we're getting, and we've defined the trigger in YAML. The other thing just to show here in YAML is here in the open application model definition, I've said I want to run this component as an auto scaler. So basically, when that's deployed, then we should have, we get exactly the same style of thing in theory, except without Azure Functions. So that was in Node again because it's easy for me, but I could have written that in Haskell or something else, as I'd required. I could have tied it up to a RabbitMQ that was running in a container in Kubernetes. I could have defined that RabbitMQ container in OAM just by defining the container, and that was a singleton or as an auto scaled, however that was set up. But I now have that running, and if I do the same thing here and we cross our fingers, 100 messages in the queue, and if Dapr is awake, it is awake. So we get exactly the same thing going on here, creates a container, and you can see because that's not the Azure Functions runtime, there's no overhead on there. That's just a pure node, a pure, very lightweight node application. So it starts processing almost immediately off that queue. We've now got up to 5 containers there, but we'll be done very quickly. And the end of that. 14, 10, 6, 5 a second. And there we go. And as soon as it finished creating the last one, it's terminating them all because it's run out of work to do. I hope that was clear enough what was going on there. So just to wrap up here, still use Azure Functions if there's nothing blocking you from using Azure Functions, still use it, because you will get something that is designed to run serverlessly, and it'll always be a step ahead of Kubernetes, even if it ends up running on Kubernetes itself, which I'm sure it will, because all infrastructure under all clouds and all things is turning into Kubernetes these days. But the good news is that with OAM and things, they're starting to abstract that. So the more that things are running on Kubernetes, the less we should need to care that things are running on Kubernetes. But yeah, if you can't use Azure Functions, then you can you set up, you enable virtual nodes to get essentially the version of the consumption plan that runs in Kubernetes. You use KEDA to get your triggers and bindings for Azure Functions running Kubernetes. For your scaling, you use Dapr to get your triggers and bindings, and you use OAM, hopefully eventually, to be able to deploy that without having to care about Kubernetes. I have no inside information here, so this is purely my own speculation. This is not NDA information or anything, but I would be gobsmacked if there wasn't something that came along at some point for you to be able to define something in OAM and run it in Azure in the same way as you can now run containers in web app for containers and just say, look, here's my web app, here's a little bit of information, run it. Or in the same way as Service Fabric Mesh at the moment, you can do a YAML definition of what your scaling characteristics are of CPU and memory. I would be very surprised if OAM doesn't eventually become something that you can deploy directly to Ali Cloud and to AKS, to Azure, as something which allows you to just say, okay, I want to define a very simple infrastructure and not care about Kubernetes at all. And if anybody is in the business of going and looking these up, KEDA, Dapr, OAM all have nice little websites there, which all link off to their GitHub repositories. Azure Functions there, if you want to go and get the public open source Azure Functions runtime that allows you to run Azure Functions in a container, that's on GitHub. And if you just want to read up around AKS in general because you can't get to sleep, then that's on docs.microsoft. And that's everything. So, any questions from anybody?
We don't have anything in the chat, Mark, but I can certainly give you a question myself. And I know a lot of organizations, and certainly we're going through the Kubernetes stuff right now. What would you say is the biggest gotcha, the biggest blocker that you found?
The biggest blocker with Kubernetes, in terms of just running Kubernetes in general, or in terms of running serverless on Kubernetes?
Kind of a bit of both, really. Where have you found that people have got stuck for the longest?
People get stuck for the longest at that point where they say, okay, we've got this running, the developers have got this thing running in containers. Okay, they've got it running in Kubernetes. Now, how do we get that running in production safely? And they suddenly discover that they've got to throw in all the service meshes and, get the secret stores set up and get everything safe. And, that's where you hit the blocker and you have to call in a Kubernetes consultant who can talk you through all this. And that's where I think OAM is going to come into its own, is that if you can just define that at a developer level, that this is my application, and then a cloud provider can hopefully then just provide a simple app service type thing that runs Kubernetes, but it's got an out of the box, okay, here's some endpoints, just expose this, and there's a service mesh in there, but you don't need to care whether that's Istio or what have you. If they can get that abstracted out, I think that will, remove, the biggest blocker, which is, like I said, just literally getting the thing to actually run in production. In terms of running serverless, sort of the biggest difference is just that, you're never going to be quite as responsive as you are in a real serverless scenario. So when people are thinking serverless, they're usually thinking about, sort of the locked in cloud versions. And I have, there's a lot of people who just refuse to believe that you can do serverless on Kubernetes. So, there's a mind share thing is a block as much as anything on running serverless in Kubernetes, I would say at this point.
I think that's the attraction to it, to be honest. I think, the ability to do that is what a lot of companies are looking for.
Yeah, I mean, like I say, there are a lot of companies that have, bet everything on Kubernetes, and, they, even though there's all sorts of wonderful cloud native services out there, they say, okay, right, we understand containers, we understand how RabbitMQ works. We'll just deploy it all into containers, put it all in Kubernetes, and then we can deploy that to any cloud we want. And then, the VC funding, there are apparently, I know I know at least one company in Belfast I was talking to, and they said the reason they were running in containers was not because they didn't want to use cloud services, but because their VC had told them that they wouldn't get funding unless they were cloud agnostic and didn't have cloud tie-in, and the only way they could do that was with containers. So.
Wow. Okay, interesting.
What are the AKS design approaches that you recommend to reduce the latency when targeting a global user base? I guess good use of CDN and front door in the case of Azure would probably be your sort of main thing there. Trying to get it to run cross region where possible. There's no magic bullet. It depends on what you're doing with it, but certainly using a CDN for stuff where possible. Ideally, if you can for the web side of things, if you can run something Jamstack so that you've got your front end running in CDN, and then have API calls coming in from that, and then if you can have your API calls distributed to somewhere close into the regions that you care about, and have those load balance using front door or something, that's probably the short answer.
Mark, I'm afraid that's all we've got time for. It's a really jam-packed session. Thank you so much for that. Really informative. And I'm sure people will be in touch with you to discuss that further. It's quite the big topic.
Mark XA on everything if you want to find me.
Thank you so much.